So we are going to continue from where we left off. Last time we were dealing with the waveguide devices, and this is one of the waveguide devices that we are yet to study and to go. Today we are going to look at it, and it's referred to as the GaN diode. With the GaN diode is that the conduction of the semiconductor is just a semiconductor, but the conduction is across the entire material. And we talk of the bulk conduction. Majority of the conduction takes place across the material and not on the GaN diode. So whatever I refer to is this, that this one now requires whatever I refer to as the applied fields, and the current is supposed to be increased at sometimes in the conduction. And for us to get a high density current, then the GaN guide will have to produce some heating effect that will now accelerate the conduction of the electrons. So the material is mainly made of gallium. Most of the time it's made of gallium. And oscillations occur due to the existence of the voltage that is put at the bias feed. So let us proceed. So this is a semiconductor. This is a semiconductor material or device in which the oscillations occur in the bulk material rather than the junction across the diode. So another thing we need to know concerning this is that the GaN effect, it requires the presence of conducting. The GaN effects requires the presence of conduction requires the presence of conducting materials, requires the presence of conducting medium. The presence of conducting medium that are separated by a semiconductor material, which is referred to as a GaN diode. So conducting medium that are separated by small energy gaps. So it also requires a voltage that is connected at the bias feed. It requires a voltage that is supplied at the bias feed. So having all this, then how does it operate? So at low applied fields, current increases linearly. At low applied fields, the current increases. The current increases linearly with the voltage, but at the threshold value, increases linearly with voltage, but at threshold values, the electrons are transferred to higher conductivity. Threshold values, the electrons are transferred to higher conductivity. to higher conductivity band, the higher conductivity band band that has a low mobility, band that has low mobility. So, the sudden collapse of the domain generates a sudden pulse that if the transmit time through the material, this is a pulse that is transmitted through the material. So therefore, if the transmit time through materials such that current pulses are in microwave frequency, the transmit materials through the transmit, therefore if the transmit time through the material is such that the pulses generated are in microwave frequencies. The power generated are in microwave frequency. Then microwave power is given out. Is given out. Then we're going to talk about also what I refer to as circulators as another device. So with circulators, we're going to have a diagram. The diagram will appear this way. So that's what a circulator appears to. And one of the things of the circulator is that when we are coupling when we are connecting the circulator to a device, the coupling is done in such a way that if the equipment is tuned to terminate at port 1, and apparently the signal frequency will go all through all the ports to where it is coupled. But the principle is that when it gets to a port 2 that the equipment or the frequency is not tuned to, then at port 2, the transmission mode is changed so that the signal doesn't come out through port 2. And the same applies port 3 and port 1. So the only time the signal will be coupled out is when the port at which it is tuned is able to match the transmission mode. So the port which is not tuned is able to change the transmission mode so that it creates a high impedance path. It creates a short circuit, and therefore it's not coupled. So until it creates an impedance for coupling, then it cannot get out of the signal. So what happens is that when the signal frequency is sent, the circular device separates the signal will move through the circulator, until it gets the right port to which it's supposed to be coupled. The other ports short circuit because it's not coupled, it's not tuned to that signal frequency. So we're going to give that in terms of details. So the circulator separates the signals by coupling the signal to the right port, by coupling the signal to the right port to which it is tuned. To which it is tuned. So we put down the operation. If the power entering port 1 is supposed to leave at port 4, then the transmission mode will change. We change at port 2 and port 3. We'll change at port 2 and port 3. i.e., if the signal was being propagated at TE10 mode, it will be changed to TM mode. So the TM mode at port 2 and 3 respectively, at port 2 and 3 respectively, so that the signal passes these ports, and when it reaches port 4, to which it's tuned, to which it is tuned, the signal reverts to TE10 mode, and so it's coupled to the output. It's coupled to the output terminal. So basically this is how the oscillator works. So if you were to transmit a signal at this point here, and the signal is supposed to come out at port 4, then if this signal will come out at TE10 mode, it's supposed to rotate in the circulator, or to move in the circulator through these other ports. But when it gets there's a port 2, This signal is transformed to another mode of transmission, maybe it's TM in this case, so that it's not coupled through port 2 and same time applies not coupled through port 3. So the signal will go through these other ports until it reaches port 4. And it reaches port 4, for it to be coupled out, the signal will now change the transmission mode to TE mode. It will revert back to TE mode so that it's coupled through the output port, which ports port 4. So basically, that's how the signal, the circulator works, and it's able to separate frequencies. It's able to give us coupling. It will be able to give us to be used as a microwave device. So what happens is that we are able to conduct through the signal the way it is. And by that case, we shall have used this to separate the signals by checking the mode of propagation. Then we're going to talk about the applications of circulators. So number one is isolation of transmitters and receivers. Isolation of transmitters and receivers. Connected to the same antenna of a radar, to the same antenna of a radar. Of a radar system. Another thing is isolation of the input and output terminals. In amplifying devices. In amplifying devices. So this is an isolator, and it has got two outputs. One of them is the rectangular waveguide, and another part is a circular waveguide. So whatever we need to understand in this one is that when we're coming the transmission frequency at a certain mode, when it gets to the transmission path, which is the isolator, then it's able to change the mode into maybe TE11 or TE10 mode. So, and then when it gets to the output, it's able to revert back. So that during that transmission, the transmission is such that this thing allows only transmission in one direction, and in the reverse direction, it creates what we refer to as high impedance or high attenuation, so that the signal can't flow in the reverse direction. So this is a device that permits an attenuated transmission. This is a device that permits an attenuated transmission in one direction while creating high attenuation. Creating high attenuation in the reverse direction. In the reverse direction. That's what we note as a basic. Then how does it operate? Then we're talking about the operation. The operation is that when the signal enters at the input, when the signal enters at the input in TE10 mode, the signal is translated to TE11 mode. TE11 mode through the device and is reverted to TE10 mode at the output terminal. Another thing we are observing here, the waveguide is surrounded by a permanent magnet. The waveguide device is surrounded by a permanent magnet which generates the required DC. Permanent magnet which generates the required DC voltage or magnetic field. So this is basically what we need to understand. So that's the simple operation of the isolator. So one of the things we are going to understand is that the rectangular waveguide is also coupled with the circular waveguide. And this one enables the translation from one mode to another before it's coupled, reverted back to the output, back to the initial mode for coupling output. So we are going to talk about the duplexer. That's all. So the final device we're going to be studying microwave devices, and it's a duplexer. And the duplexer has got the transmitter. The ATR switch is automatic transmit receive switch, the TR switch, the ATR switch. And this is transmit receive switch. So this is a receiver, but this is a transmitter. So this one is able to link this one so that we are able to transmit and receive at the same time. Another thing, this automatic transmit receive switch, this is able to connect the line automatically. That's what basically it means. But there's something good about this thing, is because it has the advantage of giving us the opportunity to use the same antenna. And another thing, it's actually just basically similar to whatever we have studied earlier as a circulator. So it operates nearly the same way. But in this case, whatever happens is that when we send a transmit pulse, then the transmit pulse, we shall have the TR switch short circuit. When the TR switch short circuits, then it creates a point of low impedance, and the signal is not coupled to the receiver. Now the signal is now sent to the antenna because of the short circuit created on the TR switch. So that's basically what we need to know. Another thing, because of that, we also have the ATR switch. You are able to connect the transmitter because the ATR switch is able to couple that to create an open circuit path so that the signal is able to move forward to the antenna. So that's what we need to understand. So it has the advantage. It has the advantage of enabling the use of a single antenna. So its operation is similar to the circulator. Its operation is similar to the circulator. So let us deal with operation. When the transmitter produces an RF pulse, produces an RF pulse. Both switches are short-circuited. Both switches are short-circuited because of the presence of the pulse. Because of the presence of the pulse or the external, because of the presence of the pulse or externally synchronized TR cells. So we need to another statement we need to put in place is that the ATR switch reflects the ATR switch reflects the pulse by an open circuit, through the quarter lambda link, while the TR switch is short circuited. And therefore, the signal is allowed to propagate to the antenna. When the signal is to be received, the ATR switch is short-circuited and creates a short circuit to the transmitter, while the TR switch is open circuited. Therefore, the signal flows to the receiver. Meanwhile, the guide leading through the TR switch. Meanwhile, the guide leading through the TR switch is correctly matched to the load. Measure. I think it goes out.